Hello. Welcome to a guide to hardware handoff using the software-hardware exchange loop, shell, flow. This video will begin by introducing and describing the shell. Then, an XSA will be generated from an AMD Vivado example design for the VEK385. Using that XSA, a system device tree will then be created. After that, the system device tree will be used to build a custom Linux build and configuration information with the gen machine conf command. Lastly, a boot.bin and EDF Linux disk image WIC will be created from the Yocto project. These files can then be used to boot the created custom Linux OS on your own VEK385. The software-hardware exchange loop, shell, flow, is a comprehensive process designed by AMD as part of EDF to facilitate the exchange of hardware and software configuration data among various open source and proprietary tools. This includes the Yocto project, Zephyr West, AMD Vitis Unified Software Platform, and AMD Vivado Design Suite. Shell allows users to mix and match tools from different vendors and versions. It defines a way for system, hardware, and software engineers to communicate about the hard, firm, and soft components of the system and their interactions. Also, it decouples hardware and software and makes sure all the different components like hardware, firmware, software, or entire operating systems stay in sync. Next, Shell allows customers to use documentation and expertise from more than just AMD. Shell enables Yocto Project, Xen, Zephyr, and OpenAMP, which are all open source tools that have many consultants, contractors, and documentation sources outside of what AMD provides. Shell also allows users to integrate AMD tools into their existing process. Shell takes AMD proprietary XSA and translates it into open source hardware description, which allows customers to pick and choose which bits of our flow they want to integrate into their existing flow or processes. Last, Shell provides safe and secure software stacks through the usage of multi-domain systems to simplify safety and security. Industry standards like Yocto Project, Xen, OpenAMP, and Zephyr are enabled by Shell. When looking at the single domain flow, Shell starts from an exported XSA file from an AMD Vivado project. From there, it extracts the system device tree for the file in SDTGen. SDTGen translates proprietary output from the AMD Vivado Design Suite into a stable, open-source, text-based format. This format is designed to be reliable and accessible for any tool, vendor, or customer. Next, a lopper takes the system device tree and applies a series of operations to that tree and outputs. This capability makes it an essential tool for managing and transforming device tree data in various development environments. Gen Machine Conf, one such example, runs within a Yocto project environment. In the single domain flow, Gen Machine Conf is used as the lopper to process and transform device tree data into Linux build and configuration information. For multi-domain flows, other loppers can be used in parallel to Gen Machine Conf to be able to target various different operating systems with the same system device tree. AMD has released Lopper to the open source community with the hope that others will use it and contribute. After the OS build and configuration information is configured, specific customizations can be made within the Yocto project ahead of generating output products that can be used to boot the board. First, an XSA file is created from a pre-built Vivado tool project from GitHub. Feel free to use your own XSA file from your own project if you are following along. The example project showing the VEK385 BRAM GPIO timer demo is available on GitHub. To be able to use all Vivado tool features, the location must first be sourced. Navigate to your desired working directory and run the following command path to Vivado settings. Run git clone command as shown to clone the full project repository to your directory. Make sure that you are using the same version of Vivado that exists in your environment to ensure a proper build. Here, use change directory command to navigate to the desired demo. This demo will use the VEK 385 BRAM GPIO timer demo, located in VEK 385 BRAM GPIO timer directory. Inside, the necessary files exist to aid in the build flow for the Vivado project. To generate the XSA file, run make XSA jobs equals 8. This will run through synthesis and implementation on the project. The newly created XSA file can then be found in the hardware project /VEK 385B RAM GPIO timer /outputs directory. Create a new directory you will use as a Yocto project build directory and move the generated XSA file to it. Next, the system device tree can be generated from the XSA file. Here, to be able to get into the SDT environment, type SDTgen and hit enter. Note, you will still need to have an active Vivado environment in your shell. Specific SDT parameters can now be entered to configure the device tree generated. Set DT param-directory. My SDT creates a directory in which your system device tree will be saved. Set DT param dashboard DTS Versal2 VEK 385 Rev A defines the target board that will be used. The target board used here is the VEK 385. Set DT param-XSA, your XSA file, will attach your Vivado project hardware to the system device tree. To make sure there is a proper handoff between device trees, run set DT param-zocal enable. To generate the system device tree, run generate SDT. Once completed, the system device tree is now generated and stored in the MySDT directory. To leave the SDT environment, type exit. Here, you can see the contents that were generated. Now, the Linux device tree can be created using genMachineConf utility. To do this, the Yocto project environment must first be set up. Note that a different shell environment should be used, so be sure to start a new environment. To set up the Yocto project environment, the first step is to set up the repo tool. To do this, grab the repo from GitHub by running curl at googleapis.com and navigate to repo directory. Next, make it executable by running chmod a+x repo. Now, a user-specific bin directory must be created if it doesn't already exist. To do this, run make directory bin. Move your repo to bin directory. To finish setting up the repo, update your path variable. Now that the repo is set up, all that is needed to be done in a new terminal to use it again is to set the path variable. After the repo is set up, a repo client can be initialized in your working directory. First, create a new directory called EDF and CD into the directory. Next, clone the Yocto project meta layer, version 25.11 or later, so that the Yocto project environment can be properly set up by running the shown command. Fetch all of the repositories by running repo sync. To finish setting up the environment, source the EDF init build environment. Once sourced, this should take you directly into the build directory, but let's take a second to see what exactly this created. Here in the build directory, a conf subdirectory exists, which contains important configuration files to assist in the creation of the Yocto project, including bblayers.conf and local.conf. A sources directory is created in the same directory that build was created. The various layers that are essential to the AMD Yocto project reside here. Now that we've created and reviewed the Yocto project environment, it is now time to create a custom Linux OS based on the system device tree previously created. To do this, copy in the pre-built template bsp.yaml file for the VEK 385 containing custom configuration information using cp command as shown to the build directory and give it a custom name like versal custom.yaml. Note that these pre-built .yaml files are new to 25.11, so using a previous release version would mean all of the parameters contained within the file would have to be run in the command line. This file will be edited to include custom parameters. To edit the file, run nanoversal-custom.yaml. When opened, the different parameter customizations can be seen. For the hardware description, this should point to the system device tree directory that was created from SDT-Gen. Next, give the machine a custom name such as Versal Custom. Last, so that the machine can be written directly to the local.conf file, include the -lconf/local.conf flag pointed to it, so the new data can be appended to the end, and save the file. Note that this .yaml file can also be created within the Meta AMD Adaptive Socks layer with adjusted paths to help better organize the Yocto project. Next, generate the machine configuration files using the AMD ginMachineConf command with a template parameter of the edited .yaml file as shown. When completed, the custom Linux build and configuration information is generated, and the boot files for the board and OS can be made. If you want to make additional customizations to the OS, you can modify the local.conf file found in the conf directory. Note that for an NFS build host system, the TMP directory should be in a valid location, such as the root/TMP directory. To generate a base EDF compatible boot image, run machine equals Versal custom bitbake Xilinx boot bin. After completed, the EDF compatible Linux disk image can be generated by running machine equals Versal custom bitbake EDF Linux disk image. Once complete, these files now reside in the TMP directory that was either specified in the local.conf file or in the tmp/deploy/images/versal custom within the build directory by default. Here you can find the boot.bin and EDF-WIC needed to boot from. In this video, the full shell flow was introduced and demonstrated. Beginning with a pre-built AMD Vivado example design, an XSA was obtained through a makefile. Then, the system device tree was extracted using SDT-Gen. From there, the Linux device tree and BSP for a custom machine was created by referencing a template file for the VEK385. Lastly, bitbake recipes were run inside the Yocto project to get the final products including a boot.bin and EDF Linux SD card image.